We shall start our discussion on hydraulic machines, and today we shall discuss about the series and parallel operation of dissimilar pumps. If we try to recall, in the last class we have talked about series and parallel operation. I mean the requirement of having two pumps or more than two pumps to be connected either in series or parallel. We have understood that depending upon the requirement, whether we need more discharge from a pumping station, and the discharge that we need, that is beyond the capacity of a particular pump. So, in that case we may have to go for series operation, parallel operation if we need more discharge, and whether we need to connect two or more than two pumps in parallel, that will depend upon the requirement. Similarly, we need to have more head that will be developed by the pump. In that case, we need to connect two or more than two pumps in series. Now, one important part that I would like to discuss today is that in fact we have seen that pump and pumping station. So, very pumping system rather. So, you know that whenever we try to install a particular pump, say if it is a radial flow pump. Now, first and foremost objective is to identify the type of pump, and that should be selected based on the requirement, and definitely if we need to calculate the amount of head that will be developed by the pump and the discharge that will be delivered by the pump will depend on the system. So, basically first of all we need to identify the system in which the pump should be installed. We need to find out the layout, piping layout. We need to find out the number of valves, number of fittings, right, number of valves, number of bends, etc. are required for that particular system, and knowing that we need to calculate the total head that will be developed. Now, question is, if we know correctly, this total head is nothing but this total head is nothing but the static suction lift H static plus H dynamic, right. Now, in this dynamic part, that is what we have seen maybe in the last few lectures, that is basically proportional to flow rate square multiplied, proportional to flow rate square. So, the proportionality constant is K. So, this dynamic head is having two different parts. One is that major losses in the pipeline due to friction, and second is minor losses due to presence of accessories. What are those accessories? As I said just now, that whenever we are trying to install a pump, we need to have flow path, we need to go for designing the piping system, and we also require valves, different types of fittings, etc. So, minor losses due to presence of accessories, that is valves, bends, elbows, etc. So, all these terms you have studied in fluid mechanics course. So, I am not going to discuss. So, basically you can understand the major loss or major losses mainly due to friction in the pipeline, and minor losses due to the presence of accessories like valve, bends, fittings, etc. So, basically if whatever may be the case, the static suction height plus dynamic, and this dynamic. So, basically this is H static plus this is nothing but K into Q square. In fact, if we try to recall, this expression is coming from the flow losses in the piping system, right. So, basically we can write using Darcy-Weisbach equation, that is F L by D V square by 2 G. Now, D is the diameter of the pipe through which fluid will be flowing, F is the friction factor, definitely V is the recommended speed typically considered in the piping system. That is what I have discussed, that recommended speed in the suction pipeline will be relatively lesser than the discharge pipeline, but in any case it varies from 1.5 to 2.5 meter per second. Now, for that particular velocity flow is highly turbulent in nature, and for that if you need to calculate friction factor, you need to look at the Moody's diagram, right. Now, also you need to consider the roughness of the pipe through which transportation will take place. So, this is basically if I try to replace V in terms of Q, eventually we will be getting Q square. So, now question is, we can understand that the total height is like this, and using this if we try to now draw the pump characteristic curve. Curves. So, I will be talking about h cube, eta cube and p cube. So, all these three different curves if we try to superimpose, say if we try to draw, so this is cube, this is h, we know this is the h cube curve, right, and we also know. So, if we try to draw using different color, so you also know if this is the static height, then this is the system resistance. Okay. Now, this is the operating point. So, this is the operating point. Okay. So, this is the operating point. Now, if we try to superimpose other curves in this plane, say this is eta versus cube. So, the curve will be like this. So, if we try to superimpose, this curve will be like this, right. So, you can understand this is the maximum efficiency point. So, if we take the projection from this particular point, this is the best efficiency point, and that is what it is written in most of the textbooks. So, this is best efficiency point, or in short it is written BEP. Okay. If we try to project it, I mean if we try to draw vertical line parallel to this eta axis, so basically this is efficiency versus cube, right. Now, question is that I will explain why the nature of the curve is like this. Now, question is, you can understand if we try to draw a vertical line parallel to eta axis, this line will cut on the h cube curve at this point, and this point is known as design point. So, this point is known as design point. Why I am trying to discuss this aspect now, let me tell you. So, this is design point, right. So, you can understand I will definitely draw the p cube curve. So, if I try to draw, I mean using red color. So, say this is p, and this p cube curve will be like this. Right. So, this is P versus Q curve. Okay. Now, question what I would like to discuss over here is that this is the operating point, because system resistance curve meets at this point, rather intersect the h cube curve, h cube characteristic curve here. So, this is the operating point. Now, the vertical line which is passing through the best efficiency point is now again intersecting this h cube curve over here, and that is known as design point. This you can understand, this design point and operating point, these 2 points are not the same point, right. It is not, I mean it would be good if the design point and operating point they coincide, I mean definitely that would be good, but depending I mean if you would like to have that these 2 points will coincide, then in that case the system designer should design the system in a more efficient, I mean effectively. So, basically whenever a system designer is designing the pumping system, he or she should be able to design the system properly, so that the best efficiency point and operating point will coincide each other. Now, question is, in this case we can understand these 2 points are not the same point, right. Okay. Next point is, so basically you have drawn H cube curve, we have also drawn eta cube curve, we have also drawn P cube curves. This is power versus flow rate, this is efficiency versus flow rate, and this is head versus flow rate. So, this is power versus flow rate, requirement of power, this is efficiency versus flow rate, and this is head versus flow rate. Okay. So, basically you can understand this is head versus flow rate, this is efficiency versus flow rate, and this is power versus flow rate. So, basically we also need to know the requirement of power, because when we are trying to calculate efficiency, and that is essentially overall efficiency, we also need to know the input power to the pump, and out of that input power what is the output power in terms of the head and discharge. So, we have also superimposed that curve in this plane. Fine. What is next important? Now, see, this is the static height, that is what we have discussed. So, this is basically H static. So, now if H static is 0, that means if we design the pumping system in such a way that there is no requirement of, I mean elevation, I mean it is not required that the liquid should be elevated, I mean at a certain height. If that is the case, then this curve should pass through the origin, very simple. So, basically if we try to go back this, I mean H cube curve. So, H equal to H static plus k into q square, right, this is H total. So, when H static is equal to 0, so when this becomes equal to 0, that means there is no requirement of having elevation, that means liquid which is pumped need not to be elevated from the pump axis to certain height. In that case it is k q square, and that in that case this curve basically representing a parabola will pass through the origin, right. So, now I will discuss very important point. Say now if I focus on this particular aspect, if we try to draw the H cube curve. So, this is H, this is Q, right. I mean if we try to draw a particular curve. So, this is H cube curve, H cube curve. When we talk about H cube curve, H cube characteristic curve, this is obtained at a constant speed. So, this curve always refers to a constant speed. So, this is at constant speed, say n1, say n1. In fact, this part I have discussed when I have discussed about pump testing. So, radial flow pump testing, if you try to recall, I told that initially the delivery valve will remain closed. If we try to open the delivery valve, speed will change. So, if we try to bring the actual head discharge characteristic curve of the pump, which is in which the speed will be changing, I mean we do not have any control over there. If we try to open the delivery valve gradually, and that is what is done in in radial flow pump testing, speed will change. So, if we try to bring the actual discharge, rather rated discharge and head, that is the discharge and head at that speed, we need to invoke affinity laws. I will be discussing this part again. So, basically if we know H cube curve, and that refers to this curve is obtained at a constant speed, say n1. So, if we try to find out, say this is the operating point, I mean say this is the operating point, and say this is A. So, this is the operating point. If we try to find out that what will be the operating point when pump is running at a different speed. So, our objective is to now to learn that this is the operating point A. Now, if the pump is running at different speed, definitely H cube characteristics will be changed. So, say this is the curve which we are getting at speed n2. So, now say this is n2. So, this is at n2. So, if we try to find out operating point, should we go to the pump manufacturer again to supply the data? No. Should we try to again do research to draw this H cube curve again? No. So, if we try to know, if we know that the pump, this is the H cube characteristic curve and that is the speed at which this curve is obtained. If we now allow the pump to run at a different speed, we can definitely calculate, we can definitely predict what will be the operating point. So, now you can understand this is the operating point. So, this is the operating point when pump is running at speed n1 and this is the operating point A prime when pump is running at speed n2. What I told? I told that it is not required to go for further research, it is not required to go for further testing to obtain this curve. Instead, what we can do, if we know the operating point which is at which is obtained from the H cube curve and that curve is generated at constant speed say n1. Now, we can apply affinity laws. So, affinity laws which is used to predict the operating point which will be obtained when the pump is running at a different speed than the rated one. So, basically that affinity law is basically q1 by q2 equal to n1 by n2. I will just for the time being you try to you accept it. I will be discussing this part again, while this h1 by h2. So, basically what I need to do, h1 by h2 equal to n1 square by n2. Say this is equation 1 and this is equation 2. So, for the time being these two different laws will be used, because we are talking about only h and q. You can understand q and q2, h and h2. Say the q1 is the flow rate which is obtained at speed n1, corresponding head is h1, right. So, if we try to obtain, say this is basically, so this is basically q1 and this is basically h1. What will be q2 and h2? So, if I try to write, if I try to draw these 2 points again. So, basically, so this is q2 and this is h2. Our objective should be to calculate q2 and h2 without going into the characteristic curve, without going into any mathematical, I mean very rigorous calculation, without going into further testing that pump, but simply by using affinity laws. These laws are well established laws. So, you can understand q1 and q1 h1 that is obtained at speed n1 and they are related to this. By what we can do now? Very nice. So, basically you can understand that we can write from these two laws. So, from 1 and 2 we can write that h1 by h2 equal to q1 square by q2 square. So, n1 square by n2 square, so that is q1 by q2 square, right. That is what it. So, basically from this equation we can write that h1 equal to h2 into q1 by q2 square. So, that means if we know the speed n2, then simply we can calculate q2 at when the pump will be running at speed n2, right. If we know n2, so pump is developing head h1 when running at speed n1. Now, we can easily calculate using equation 2 what will be head developed by the pump when running at speed n2. Using these two equation we are getting this equation. So, basically this equation simply tells us that this h is proportional to q square. Now, this is the equation 3. What does it represent this equation? You can understand this is the equation of a parabola and passing through the origin. So, basically I can tell you that q1, q2, h1, h2 basically these are the similar points, but operating at a different heads. So, if we try to find out the locus of similar points at different speed, and that those points will lie on a parabola, that we can see from equation 3, right. q1, q2 and h1, h2 basically those are the similar points, that is operating points, right, but those are obtained at a different speed from the same pump. Now, the locus of all these points are passing through a parabola, provided the static height, I mean what we can understand from this two equation, we can understand all similar points of the will lie on a parabola when pump is running at different speed, right, and that is obvious from equation 3. What we can see from this H cube curve, so this is the system resistance curve. So, let me tell you this is the system resistance curve. So, this is system resistance curve. So, basically all similar points on the different characteristic curve, right. So, this is the point A and this is the point A prime. So, all similar points on different characteristic curve will lie on a same curve, that is parabola. What I said just before, just 2 minutes back, all similar points which are obtained at different speed, that means these points are definitely lying on different characteristic curve, we will follow this equation parabola. Now, you can understand from this system resistance curve, can't we say that all these points will passing through origin if the static height. So, basically you can understand this is the equation of parabola, this is the equation of parabola, but this I mean if we make the static height. So, this is a static, if we make the static height is equal to 0, then we can say that when static height is equal to 0, all similar points which are obtained at different speed, in other words all similar points on different characteristic curve will pass through parabola provided the static height is equal to 0. So, these two statements are correct, right, these two statements are equal. So, basically what we can see that when static height is equal to 0, if we know the discharge and head from a given speed, we can easily calculate what will be the h cube, that is the head and flow rate at a different speed. Okay. So, this is what I wanted to discuss in today's class, you can understand. So, this is the parabola equation, but this is the parabola equation which is passing through origin, that is what we have learned from 10+2 mathematics, right. Now, from this particular curve again we can see this, if this static height becomes 0, then definitely all the similar points which are obtained at different speed, in other words again I am telling all the operating points on different characteristic curve will pass through parabola, that is h is equal to q square. So, basically it simply indicates if we know the head and discharge at a given speed, then simply we can calculate the head and discharge will be delivered by the pump at a different speed using this equation. Okay. Now, what we can do quickly, we can discuss about the important point, that is what I wanted to discuss today, that is the h cube curve when two dissimilar pumps are connected in series and parallel, right. So, this is what I am going to discuss through graphical representation, right. So, what I have discussed in the last class, we have discussed that it is very much obvious that very often you need to go for series and parallel operation of the pump, and that is depending upon the requirement. Now, as I also discussed that it is very unlikely that when there is a need of two pumps to be connected either in series or parallel, we will be getting two similar pumps, because one pump is already installed there, and after 10 years or 12 years down the line depending on the requirement, or 5 years down the line, if we need to connect another pump with the existing pump either in series or parallel depending on the requirement, it is very unlikely that the newly pump that will be procured from the market will be of similar type, will be of similar design. So, it is very likely that we will be getting another pump, maybe we will be getting similar type of pump, that is radial flow pump, but their design are not same. So, basically what we need to consider, we always need to look at that if we need to connect two dissimilar pump here refer to the pumps which are not of same design, but they are of same type. It is not that we are trying to connect one radial flow pump with the one axial flow pump, this is not the case, but this is the case wherein these two pumps are not of same design. So, first case, so if we consider now case 1, as I said we will try to discuss through graphical representation only. Okay. So, first case when two pumps, of course again I am writing dissimilar, that is not of same design are connected in series. So, this is quite very interesting point that we should now consider. Okay. So, when two pumps dissimilar, again to sort out the confusion if any, that the dissimilar is not that one is radial flow, other is axial flow, or other is mixed flow. So, basically they are not of same design. Okay. So, let us first draw the H cube curve of a single pump. So, this is H, this is Q, and this is H. Say this is one pump, and if we try to draw the schematic depiction of other pump, say this is the other pump. So, this is say this is pump 1. So, I am writing this is B and this is A. So, this is pump A and this is pump B. You can understand the design of these two pumps are not same, and as a result if they are of same type, H cube characteristic curve will coincide each other, but this is not the case. Now, if this is the case and they are connected in series, what will be the characteristic curve of the combined pumps? So, what we know, what we have learned from yesterday class, what is the procedure? If they are connected in series, as I told you that the flow rate that will be discharged by the first pump will be taken to the inlet of the second pump, and eventually the total head that will be head developed by every pump, every individual pump will be added together. Fine. Now, you can understand. So, basically for a given head, flow rate will be for a given flow rate, head will be added together. So, fine. I mean, if we try to draw now, because I have to so this is basically this is the H cube curve, right. Now, you can understand this is the sort of it. So, if we join together, so you will be getting. So, if we try to draw using red color, so this is the line. Now, you can understand. So, this is say I am talking this is the cube n. I can take this is cube 3, I can take this is cube 2, I can take this is cube 1. So, what is the procedure for a given flow rate? Head developed by an individual pump will be added together. So, basically, so the head developed by each pump will be added together to obtain the total head from the system. So, basically you can understand if we try to for a given flow rate Q1, if we try to obtain, so this will be the point. So, this will be the point, for this maybe this is the point, for this will be the point, for this will be the point, understand. So, we will be getting the curve like this. Now, what will happen after the point Q n, because this is the last point. So, we have taken only 4 different points. If you take more number of points, curve will be smooth. Anyway, so after this point there is no flow rate developed discharged by the pump B. So, basically if we again try to connect, I mean this curve, the combined H cube characteristic curve will follow the same line, right. So, the system will deliver head. So, if we try to obtain the flow rate corresponding, say this is the flow rate we need from the pumping system, then head developed by the pump will be the head which will be developed by the pump A, because the contribution of pump B will not be there after this particular point. So, this is the combined H cube characteristic curve. So, this is H cube curve of combined pumps. Okay. So, you can understand, again I am telling after this point. So, this is the point, after this point there is no flow rate that will be supplied by pump B. So, there no point of having addition of head. So, basically after this particular point, so this line will cut over here, after this point the combined H cube characteristic curve will follow the characteristic curve of pump A, and that is what. Okay. Now, when the two pumps are connected in parallel, so again let me draw. So, if we try to draw the H cube characteristic. So, this is cube. So, this is H. So, when so this is case 2, when pumps are connected in parallel. So, if we consider these two pumps again, so maybe this is the characteristic curve of pump A. So, this is for A, and if we use this color to obtain for B. So, this is for B, right, and if these two pumps, I would like to say these two pumps which we had considered for I mean to obtain the combined curve combined pumps characteristic when they are connected in series, we are considering the similar these two pumps again. Now, for the when pumps are connected in parallel, what I have discussed, basically the procedure is ultimate objective is to increase flow rate, right, that is what we have learned from yesterday's class. So, now what we can do, for a given head the flow rate delivered by each pump will be added together to obtain the total flow rate. So, now we can understand in this particular head. So, I mean for a given head, so up to this. So, now if I connect, if I use red color, so you can understand up to this point there is no head that will be imparted by pump A. So, pump A will be able to, the sort of head of pump A is from here. So, up to this point, though these two pumps are connected in parallel, combined curve will follow the curve of pump A, right. So, this this curve pump will start from here up to this point. So, this is the sort of head, ideally sort of head will start from this point, and then if we consider at least this is H 1, this is H 2 and this is H 3. So, this is H 1, H 2, H 3. For a given head we will be adding the flow rate supplied by each pump. So, you can understand this plus this flow rate. So, it will be here, this point will be here, this point will be here. So, after this point curve will be like this, right. So, again I am telling this part. So, before this point, so this is the sort of head of pump A. So, up to this point, so I am giving this particular cross mark, up to this point the H cube curve of combined pumps will follow the similar trend of the similar trend which is the curve which is the characteristic of pump B. After that, just we need to add the flow rate for a given head and then we will be getting this curve. So, this is the H cube curve of combined pumps. Okay. So, I hope I have been able to explain the when two dissimilar pumps are connected in series and parallel, then what will be the characteristic of H cube curve, and that is what we have tried to explain graphically. So, basically if we try to summarize today what we have done, we have tried to understand that if we try to calculate the operating point when a particular pump is running at a speed which is different from the rated speed. So, basically whenever any particular H cube curve is referred, that curve corresponds to the rated speed, so constant speed n 1. Now, if we try to obtain the operating characteristic curve from the similar pumping station, we should not go for further testing, we should not go for further investigation of drawing the H cube curve, rather we can simply apply affinity loss to obtain the design points when the pump is running at a different speed. And finally, we have tried to discuss that when two dissimilar pumps are connected in series and parallel, then what will be the combined H cube characteristic curve. So, with this I stop here today and we shall discuss in the next class. Thank you.